All right, welcome. We're going to be looking at lesson 1 here, the mean value theorem. So we're going to go ahead and read this scenario that we have. Police officers use a variety of techniques to assess drivers' speed and issue speeding tickets. Many people have tried to argue in court these devices are unreliable. Does calculus have an answer? So we're going to be looking at something called the mean value theorem. If we sort of like kind of parse those words, right? Mean is another word in math that we use to say the average value theorem. So we're going to be looking at the average rate of change, kind of like, slope on certain intervals, and we're going to figure out if that can tell us information about what's happening in particular instances. So Leanne is driving east on Reagan Memorial Tollway in Illinois. 2 weeks later, she receives a speeding ticket in the mail and a printout of her Easy Pass records, and you can see those right here. We have these different toll plazas, the mile marker on the highway that they're located at, and the time during which she passed through those things. So let's go ahead and try to answer some of these questions. First question says, how many hours did it take Leanne to make it from Rock Falls to Maple Park? So we're looking at this trip here from Rock Falls to Maple Park. And time-wise, we can see here from 1:23 p.m. to 2:11 p.m. is the time that we have there. And if we do our calculations, right, that's an increase of 48 minutes. So it does ask us in hours, so we're just doing a quick unit conversion there. So we would do 48 minutes times 1 hour over 60 minutes, right? Or that's sort of equivalent to dividing this by 60. Our units for minutes would cancel out, leaving us with units of hours. Anyway, we do a quick calculation there. 48 divided by 60, we get that this is around 0.8 hours, or rather exactly 0.8 hours. Question 2, what was her average speed between Rock Falls and Maple Park? Okay, average speed, right? We don't know exactly how fast she was going at any given instant, but we can calculate her average speed by taking her change in distance, right? How far did she go, divided by the change in time. And luckily we know both of those things, right? The distance, she went from mile marker 45 to mile marker 100, so that is 55 miles in 48 minutes, or 0.8 hours. So we're going to go ahead and calculate that. That would be 55 miles. Oops. We'll just fix that. MILES divided by 0.8 hours, and that will give us miles per hour. So we do a quick calculation there, and we're going to call this 68.75 miles per hour. So that is her average speed. Again, that doesn't tell us specifically how fast she was going at any moment, but that this was her average speed, which is fine, right? Now, question 3, if the speed limit is 70 miles per hour, is it possible that Leanne was speeding during this time period? Please explain. All right. So again, we calculated the average speed. So if we know that she was, going around this speed, but it is possible, based on the way that averages work, it's possible that during some time she was going faster than this, and sometimes she was going slower than this. So in this case, the answer would be, say, yes. It is possible that at various times she was traveling faster or slower than her average speed, right? And yeah, that's kind of like enough information because this number that we've calculated, it doesn't say that that's exactly how fast she was going at that moment. She could have gone much faster for a short period of time and then a little bit slower for the rest of her trip. But this average gives us some indication of around what speed she may have been traveling. Okay. Question number 4. Do police officers have convincing evidence from the Easy Pass alone that Leanne was speeding between Rock Falls and Maple Park? Okay, this is an interesting question. Is this evidence that she was speeding or not? And the answer here is, well, no, right? Because we only know her average speed, which was below the speed limit. So there's no way to know that she didn't just travel at this speed, the entire time. That she traveled at a constant speed the entire trip, right? So this alone here is not convincing evidence of her speeding. Again, because she could have just been going that constant speed the whole time. All right, let's go ahead and move forward here. How many hours did it take Leanne to go from Maple Park Plaza to Elmhurst Plaza? So we're going to look at that second leg of her trip, and we're also going to calculate the average speed between there. So we're going to do kind of the same thing that we just did, but we're going to be looking at this next section of the trip. So from Maple Park to Elmhurst, she traveled a total of 40 miles. So we'll go with that, 40 miles, and the time that it took her from 2:11 p.m. to 2:40 p.m., right, that's going to be 29 minutes. All right, so we're going to kind of use those numbers here to do our calculations. So first of all, how many hours did it take her? We're going to do a quick unit conversion of that, 29 minutes, right, times 1/60. And that one's not going to be an exact one here, so we're going to go ahead and round that to 0.483, and that would be in hours now, right? Because this is hours, this is minutes, minutes cancel, left with hours. So that's how long her trip was. And again, are going to calculate that average speed, so we need her change in distance, which was 40 miles, divided by the time that we have here, 0.483 hours, and then we're going to do a quick calculation with that. So we got 40 divided by 0.483. And I get an average speed of 82. I'm just going to round this to one decimal place. Again, we usually do 3, but for right now, this is good enough. 82.8 approximately miles per hour. So again, this is her average speed, or at least, a very close approximation for that. Alrighty, now they've got her, right? This average speed, that's too fast. Do the police officers have convincing evidence from the easy pass alone that Leanne was speeding somewhere between Maple Park and Elmhurst? How do we know? Yes. Yes, they do. Because her average speed was greater than, the speed limit, we know that she must have been going more than 70 miles per hour at some point during the trip. Likely for most of it, right? If her average speed here is significantly greater than the speed limit, which it is, 82 miles per hour is significantly greater than the speed limit, which was 70, we know that she was probably going more than that speed for most of the trip. So, must there have been a moment in which Leanne was driving exactly her average speed? How do you know? Interesting, right? So this is a really important idea that we're going to be looking at. This is something that we call the mean value theorem. So, must there have been a time where she was traveling her average speed? Yes. The answer here is just a short answer. It's yes. Sorry, I'm going to change that font size. Yes. At some point, right, instantaneous, she had to have been traveling at exactly her average speed. So let's go ahead and talk about that just really briefly here. If she's averaging 82.8 miles per hour, right, it's possible she's going faster than that. It's possible she's going slower than that. But if she's going slower than that, at some point, in order to average out to 82, she also has to go faster than that, right, at another point. So it's impossible for her to be going slower than 82.8 at one point and then faster without at some instantaneous moment having traveled exactly her average speed, right? Or if we look at it the other way, right? We know she was going faster than her average at some point. That means that in order to make up for that and average to this average speed, that she had to have also gone slower than her average speed at some point, which means she had to have slowed down, passing through her average speed at least at some instant. And it's possibly likely that she was even doing it more than just one instance. Anyway, this is our mean value theorem. And basically the idea of the mean value theorem is exactly this, that the average rate of change has to be equal to the instantaneous rate of change at some point on an interval here. So in our case, her average speed had to have equaled her instantaneous speed at some point. Anyway, let's go ahead and look at our more formal notes on this. So here we have our mean value theorem stated more technically. It says if f of x, if a function is continuous and differentiable, so continuous on an closed interval a to b and differentiable on an open interval from a to b, then there is a c value such that f prime of c, the instantaneous rate of change at c, is equal to this over here, which is our average rate of change, right? This is the average rate of change on an interval, f of b minus f of a over b minus a. Now, when we're looking at the mean value theorem, we have the condition that we need to make sure is true. So this top line up here is our condition, the if part. So if we have a continuous function on a closed interval and it's differentiable on the same interval but open, then this right here is our conclusion. Then there is some value c where the instantaneous rate of change at c equals the average rate of change on the entire interval. Now, let's take a look at the graph and sort of see how that plays out on a graph. So here we have a quadratic function. This looks like a quadratic function, right? A parabola. And let's just say we pick some sort of an interval. We'll call this our a value, and we'll just go b over here. Obviously, it is continuous on the interval, right? We can kind of follow it along. We can see there's no discontinuities there. Yes, it's possible that there could be a hole that we're not seeing, but we're just going to assume that there isn't. And it is differentiable, right? The slope, as we look at it, is kind of nice and smooth and continuous, right? There's no weird things happening with the slope of our graph. So that means that the average rate of change, which would be a secant line that goes from here to here, so this would be our average rate of change. That's this part over here, f of b minus f of a over b minus a, right? The slope of that has to be equal to the instantaneous rate of change for some value inside this interval. And so it's kind of hard to see, but I don't know, maybe kind of up in this region, if we were to sketch out a tangent line, that tangent line would sort of match. Again, it's sort of hard. Let me just take this line and then I'll try to like move it around. So I'll click on it here and we'll kind of drag it around and see where it might fit on the line. Okay, yeah, maybe I kind of missed it a bit, but if we look, yeah, maybe right about there. So if we were to graph it, right, maybe this point. And so that would be the C value that is guaranteed by the mean value theorem. That would be our value C. It's actually kind of almost right in the middle of the interval that I matched. But anyway, this is our instantaneous rate of change, right? This tangent line. Well, the slope of this tangent line, maybe fix that line, is going to be equal to the slope of this secant line, right? And this is a secant line. It hits our graph in two spots. So these slopes match one another. And this is what the mean value theorem guarantees. Again, that's our conclusion of our mean value theorem. All right. So let's go ahead and quickly just sort of go over, how we use something or how we prove something using the mean value theorem. There's kind of 3 steps here. It says 1, check the conditions. So we need to check that it's continuous and differentiable. Now, One of the nice things about this is actually you can just check differentiability, because if something is differentiable, it is continuous. Now, if you don't remember how to check if something is differentiable, there's a few things to sort of look at, but one of the best ways is looking at the graph of the derivative if you have access to that, but you may want to look back at how to do that. You can also check continuous easily by looking at the graph of the function. Anyway, once you've met the initial conditions, it is continuous and differentiable. The second step is you want to find that average rate of change, right? So you find that average rate of change on your interval. So you do f of b minus f of a divided by b minus a. And now there may be some other things that you need to do in this, right? You may need to figure out where, figure out that c value, find the value that your derivative equals this average rate of change. But that sort of depends on the question. And then finally, 3, you need to make your conclusion, right? So in this part is the conclusion. So you need to say there is a number in this interval where the instantaneous rate of change equals this average rate of change value that we did. And you want to make sure to kind of restate whatever the question stem is. That includes, the context of the scenario or kind of whatever's happening there.